In this video, I will discuss a JEE Advanced PYQ based on the topic Work, Energy and Power. The conservation of energy says the initial energy of the system and the final energy are equal. But suppose the work is done on the system, then the final energy will be more by an amount of the work done. And if the system does work, then the final energy will be less. So work done by the system should be added to the final energy to match the initial energy. So this is work energy theorem. Another basic concept that is used in this question is energy is stored in the spring. So this is a spring which is fixed at one end. So this is a natural length spring. And suppose I compress this spring by an amount, say x. Suppose the spring becomes like this. Say the amount of compression is say x. Then the energy stored in the spring is half k x square, where k is the spring constant and x is the amount of compression. Similarly, the spring can be stretched by an amount, say x. So compared to the original length, say the stretching of the spring is x. Then again the energy stored in the spring is half k x square. Now the basic thing is work done by a force when it produces a displacement ds is dw, and is the dot product of two vectors, force and the displacement. So with these basic ideas, we can solve this JEE Advanced question. Timestamps are given in the description box. You can watch parts of video if you are running short of time. This is the question. A block of mass 0.18 kg is attached to a spring of force constant 2 Newton per meter. The coefficient of friction between the block and the floor is 0.1. Initially, the block is at rest and the spring is unstretched. An impulse is given to the block as shown in the figure. The block slides a distance of 0.06 meter and comes to rest for the first time. The initial velocity of the block in meter per second is v, which is equal to n by 10. Then n is. You can pause and attempt this question. This is a simple question. So as soon as the impulse is given, the block will pick up a speed. So this is at a time delta after the impulse is given. So let the velocity at this instant be v, which is given in the question. And then the block will compress the spring until the velocity of the block becomes 0. So finally the block will come here and the velocity of this block, let me call it v1, becomes 0 because the spring will try to push the block in the opposite direction of the motion. So this distance is x and that value is given as 0.06 meter. So the block moves by this much distance before it becomes 0, before it stops. So we define this velocity and there is friction force between the block and the surface. So initial energy of this block is the kinetic energy, which is half mass of the block and then v square. There is no other form of energy. Initially the spring is unstretched initially. So the energy stored in the spring is 0. In this portion, the spring has got compressed by an amount x. So the energy stored in the spring, the final energy of the system is energy stored in the spring is half k x square, where x is 0.06. And the kinetic energy of the block in this final portion is 0 because velocity is 0. And work is done by this block to overcome this friction. So work done by the system. System is the block and the spring. This f dot ds integral. Here the force and ds are opposite directions, cos 180. So it's actually a uniform force because friction force is uniform, so it will come out. So integral ds is the total displacement, which is x. This friction force is coefficient of friction mu into the normal reaction and the normal reaction between the block and the surface is the weight. So it's mu mg. So initial energy So work energy theorem, initial energy and final energy. Because of the work done by the system, the final energy will have reduced. So if I add this work done by the system, it will match with the initial energy. This is work energy theorem. Initial is half mv square. Mass is 0.18. V square, V is the thing we have to find out. Final energy is the energy stored in the spring. It's half K, spring constant K, which is 2 Newton per meter. X square is 0.06 square plus the work done. Mu is 0.1 and mass of the block. Mu is 0.1. Mass of the block is 0.18. This is the friction force. Mu is 0.1. Mass of the block is 0.18. G, I think it's 10 into the distance 0.06. G they have not given, but let me take it as 10. So here only one unknown is there, V, that you have to find out. So this is 0.9 V square equal to 0.06 square. That is 36. 0.9. Okay. Plus this and this will give me 1. 0.06. This is 0.06 into 3. Okay. So here there is 1.0. So 36 into 10 raised to minus 4. 0.06 into 3 times. So 3 plus 1, 4. This is 0.06 into 3. Okay, it's just 3, no? So 4 times 36 into 10 raised to minus. So here we have 9. Yeah. So 0.1. So V square into 0.1. 4. 4 square into 10 raised to minus 3. Some mistake is there. 0.09. So become 10 raised to minus 2, then it's easy. So this is 4.4. So what they are given in the question is velocity is n by 10. So this we have to compare with n by 10. That means n is 4. Four is the correct answer. This is what I explained here. Work energy theorem, initial energy is equal to final energy. Work done on the system will increase the final energy by an amount of work done, and work done by the system will decrease the final energy. So if we add this thing to the final energy, that will match the initial energy. Initial energy of the system is the kinetic energy of the block, half mv square. Final energy is the energy stored in the spring, because the kinetic energy is 0. Initially, the energy stored in the spring is 0. Work done by the system is to overcome the friction force. The friction force mu in the normal reaction, which is mg, into the distance traveled, it's 0.06. So half m is 0.09 v square, half k is 1 because k is 2, is given in the question. X square is 0.06 square, and mu is 0.1 given, mass is 0.18, and g is 10, and this is 0.06. So if you do this simple calculation, v will come out to be 0.4, which is 4 by 10. If you compare it to n by 10 given in the question, n is 4.